Hello, welcome to Deterministic Optimization. My name is Shabi Ahmed. I'm one of the co-instructors of this course. So in today's lecture, we are going to examine the information provided by the linear programming relaxation of an integer program. Let's get started. So here is a mixed integer linear program. So we have a decision variable x, which has some components that are required to take integer values, and the remaining components can take continuous values. And we are interested in minimizing a linear objective subject to some linear inequality constraints. So this is our mixed integer linear program. Its linear programming relaxation, and we have talked about this before, is obtained by simply dropping the integrality restrictions on the variables. So this is exactly the same problem, except for the fact that our decision variable now is taking all the components to be continuous valued. So this is now a linear program, right? So this linear programming is very intimately related to this mixed integer linear program, and we're going to see how that happens. Okay, so just let's start with an example. So here's an example in 2D. So here we are interested in minimizing x plus y. So part B, there should not be any kind of subscripts here in this particular thing. So we are minimizing in x plus y, subject to the constraint that 3x plus 2y is greater than or equals to 6, and x plus 4y is greater than or equals to 4, x is between 0 and 3, y is between 0 and 3, and x and y are integers. So if you plot out these constraints, you will find this shaded polyhedral region as the feasible region, and we're interested in the integer points, or the points which have integer components, which are denoted by these blue points. Those denote the feasible solutions to this integer program. The LP relaxation is simply obtained by dropping the integrality restriction. So in other words, the LP has a feasible region which is given by the entire shaded brown region. Once we solve this linear programming relaxation, we get the solution x1, x is equal to 1.6 and y is equal to 0.6. So now what information we can get by solving the LP relaxation? Now clearly, because it is a relaxation, if the LP relaxation is infeasible, then clearly it follows that the integer program is also infeasible. Now the second bullet point, as long as the data is rational, and we are going to always be talking about rational data, it turns out, and we are not going to show this, but it is a delicate result which shows that if the LP relaxation is unbounded, then either the integer program is infeasible or it is unbounded. If the LP relaxation has an optimal solution, then it is possible that the IP could be infeasible or have an optimal solution, right? So it is possible that the integer program is infeasible, right? So let me just give you kind of a simple example. So suppose I want to solve this integer program, right? X is between a half and a 3/4, and x is an integer. So this integer program is infeasible, but if I drop this integrality restriction, the LP relaxation is feasible and has an optimal solution. Right? So we have to be careful about that. Nonetheless, it always holds that the optimal objective function value of the linear programming relaxation, VLP, is less than or equals to VIP for minimization problems, right? Because LP is a relaxation, it has a larger feasible region, so the objective function value can be at least as good as of the optimal objective function value of the integer program. So therefore, if an optimal solution of the LP relaxation is integral, what does this mean to be integral? It means that whichever component is supposed to be integer, if it turns out luckily that they're actual integers, then it must be an optimal solution to the original integer program. So the LP relaxation provides quite a bit of information, as we have just seen. It also provides a way to estimate an optimality gap of a given solution to an integer program. So let me illustrate that with an example. So now let's go back to our example in the previous slide that we had just talking about, and consider the solution given by 2, 1, which is this point here, right? So this solution is x equals to 2, y equals to 1. Clearly this is a feasible solution. Now, how good is this? Is this a good enough solution for the integer program? Well, obviously we do not know this unless we solve the problem, but we can compare it to the objective function value of the LP relaxation and get an idea of the optimality gap of this solution. Recall that the LP relaxation has an objective function value of 2.2, we know this, and this particular solution, we can compute its objective function value, that's 3. So I know that the optimal value of the integer program is a number which is between 2.2 and 3. We do not know what it is, but it is between 2.2 and 3. So therefore, the optimality gap of this solution is at most 3 minus 2.2, right? So we know that 2.2 is a lower bound on the optimal value, so you cannot be more than 0.8 units away from an optimal solution. So this gives us a very easy way, just by solving the linear programming relaxation, how we can give a qualitative guarantee on a given feasible solution. Sometimes it is also possible that the LP relaxation solution can be rounded to get a feasible solution and a good feasible solution to the integer program. So here we have one example where this is the LP relaxation solution, and if you round it to the nearest integer, so it could be this one, that one, or that one. In this case, the nearest integer turns out to be this one. This nearest integer solution turns out to be feasible. And in fact, for this example, you can check that this is actually the optimal solution of this integer program. Now, obviously, this was, by luck. It is possible that this does not work. For example, here is another linear program, and these are the integer points in that linear program. If we solve the linear program, we get this solution. And if we round it, for example, to the nearest integer, we're going to get this point, which is not feasible. Even if we round it to any of the closest integer, this point, or that point, none of those are feasible. So in this case, we are not able to round this solution to get any good solution to the integer program. Okay, so let's summarize what we have just discussed. The LP relaxation provides valuable information about an integer program. Its optimal value provides us bound and therefore an estimate of the optimality gap. Its solution can sometimes be rounded up or rounded down depending upon the feasibility to a good solution to the integer program. Okay, that concludes this lesson. See you in the next one.